Chemers. Today's video is on the evidence of arson. And so this is an interesting field that has changed quite a bit over the past several decades, probably the last 30 years. And so we'll get into some interesting topics today. So whenever there's an arson or some sort of an explosion, it's pretty difficult to find the evidence. Sometimes the circumstances are tough. What's interesting too is a friend of mine who's an arson investigator, he said that he calls the fire department the evidence destruction department because whenever there's a fire, one of the questions is always, was this accidental or was this intentional? And so they must come in and identify the relevant chemical materials. If there was an explosion, they must see if that was like a boiling liquid explosion or if it was detonated with some device. So they'd be looking for igniters or timing devices, and then they have to try to reconstruct the event. So this is a bit difficult because so much of the evidence is destroyed, but not always. Not every bit of evidence, as we saw in the last video on explosives, how they were able to find bits of the circuit board used to bring down Pan Am Flight 103. And that was an explosion that happened in the air, and the plane was destroyed into about 10,000 pieces, and yet they still found the luggage that the bomb was in, and they found the circuit board of the cassette player that the bomb was inside, and the timing device. So for fire investigation, it's really difficult. As I said, so much of the evidence is destroyed. And so you want to identify where the fire started. And did it start on the first floor? Did it start in the attic? Was it electrical and so on? When I say, was it intentional? If it was the first floor, heat rises, and so it's going to be very easy to find that it started on the first floor. Maybe, if the fire is fully involved in the building and it started on the upper floors, the evidence may be totally destroyed as to what started the fire. Let's look here at a house fire. And so this is a good example of what we call a V pattern for the fire. So you can see that this is obviously started over here in this red circle. You see kind of a V to the heat damage from the fire. Like these are some like polyester or cotton curtains over here. There was a fire in this room and these curtains are undisturbed. They might have a little smoke damage, but no heat made it over here. The heat obviously started over here because of the charring, and you can see kind of a V pattern. These curtains were melted or cooked in some way. And then the ceiling, you see a little smoke damage made it over here. So that's a huge V pattern, and that V will point to the origin of the fire in many cases. So let's zoom in on this little red square. Was this intentional? Was there gasoline poured in the corner of the room and then they closed the door and left? And maybe even lit it so it would go underneath the door. That's one possibility, but let's see what we find if we go into this corner. So behind that door, we see a lot of debris that came off the wall, so maybe some wallpaper that burned and fell down, but maybe there's a little more debris. Maybe there's like charred magazines and things, and then this looks like a burned electrical outlet. So maybe that electrical outlet got hot enough to catch these papers on fire. There's it looks like some wet debris here. Maybe there's some arson relevant evidence there. So if you were to come into this as an investigator, you would want to pick up some evidence, dig it to the bottom of this ash pile to try to find if an accelerant was used. And so you could have an arson can, an evidence can, and we'll see some of those in a later slide. And you would use tweezers and gloves, and you would pick up the evidence, put it into this airtight can, hammer the top, it's like a paint can, hammer the top shut, and fill out the location of where you collected the evidence and so on. And then you would take that back to the lab to see. But this was most definitely the source or origin of the fire in this structure. So we can look at the fire scene. You begin examining a fire as soon as the fire department will let you in there. In fact, many of the arson investigators are firefighters. So as soon as they think the room is stable enough to go in without the the hoses blaring, then you can come in and start your investigation. Experience shows that most arsons are started with petroleum-based accelerants, and so that's going to be your most common indicator of an arson, is something that's combustible or flammable. Now the difference between combustible and flammable is the flash point. So if it has a flash point below 100 degrees Fahrenheit, then we call that substance flammable. But if it's not flammable, that does not mean it won't burn. Like diesel is listed as combustible because its flash point is above 100 degrees Fahrenheit. All the flash point means is that the flame, if you have a pool of fuel and you have a flame nearby, that the flame will spontaneously jump from the flame to the pool of fuel and burn across the top of the fuel. It will flash across the top of the fuel. And you have to elevate the temperature of that fuel to above its flash point for this phenomenon to occur. And so 100 Fahrenheit is just an administrative number that we set. So if it flashes at temperatures lower than 100 Fahrenheit, then we call that flammable. And if it's above 100 Fahrenheit, we call it combustible. And so you might find petroleum-based accelerants soaked in to carpet or paper, or maybe the wallpaper if it was splashed onto the wall. And so you would look for those petroleum-based signatures in your subsequent forensic analysis. So then there's such a necessity, because these petroleum-based accelerants are volatile and you've been in a hot environment, the chances that they will evaporate and the evidence will be lost are high. So this is one example where the investigation takes precedence. So if there's been a fire, the fire department has responded, the door is now open for the arson investigator to come in and investigate arson. They can begin that investigation immediately and don't have to wait for a search warrant. The search of the fire scene must focus on finding the origin, and so that's where we're going to find most likely evidence of an accelerant if it was an intentional fire or some sort of ignition device. There are some telltale signs of arson, like if they have streamers on the floor. So sometimes oil-soaked rags can connect the fire from room to room, or even ropes, or most commonly just pouring gasoline along the floor where the fire will spread across that gasoline streamer. This is a telltale sign. So you'll have multiple origins for the fire. You'll have V-shaped charring in multiple rooms, or you'll see burn patterns on the flooring. And normally the fire has a tendency to move in an upward direction, and so we can find that V pattern and look at the bottom of the V for the source of the fire, or the origin of the fire. And so, interestingly, combustible liquids are rarely entirely consumed during a fire, so there's almost always some residue left behind. And this is the real key for arson investigation. This is an NIJ report that's available on the Blackboard site, and this is pretty interesting. They have a fire testing laboratory that has a warehouse. It's got like a concrete pad that they can put flooring and other kinds of things on, and then they have a giant hood that sits above that pulls all the smoke and everything up through some scrubbers, and so they can work in that warehouse while a fire is going on and not be exposed to the smoke or anything like that. They can put thermal imaging on there and measure the heat that comes from different materials. They can measure the heat of the smoke. They can look at these burn patterns. And so this is a really cool report to read through. You're not going to be tested on this whole report. It's many, many pages, but there are some interesting conclusions for arson investigation. One thing that we'll see is burn patterns on the floor. So here's a picture of the flooring that they put. This is in their warehouse. There's a hood vent up above this, and so all the heat and the smoke are going up into the hood, so they can set up their equipment and work in here while a fire is going on and not be in danger. What they wanted to do in this report is to see if they put a gallon of gasoline on the fuel, what size ring would it make? And then they would set it on fire and see if the burn pattern matched the liquid ring size, and if that could be tied to the volume of gasoline that they poured on. Now, most likely in carpet, that's going to be the case, but what about tile floor? So here's like a linoleum tile floor. Here's a parquet wood floor. And so they poured gasoline on these different types of flooring, set them off, measured the charring, and looked to see if there was residue of the accelerant in the flooring. And it's, like I said, it's a fantastic report. So here are some conclusions from this report. The spill area can be predicted by the fuel quantity. And so if you look at the size of the spill area, it's going to be bigger, obviously, if you have a larger amount of fuel poured on that surface. And so the carpet burn areas were found to be the same as the carpet spill areas. Notice burn and spill are two different things. So the spill area maybe was like 2 feet across, and then the burn area was also 2 feet across. So this was a match in terms of carpet. So when you look at the burn area on carpet, you can assume that that's how big the spill area was. So if it's a tiny little spill area, then it may be accidental. If it's an enormous spill area, then you probably have someone trying to set the fire. So you would have to evaluate the totality of circumstances as well to see if there was other indicators of insurance fraud. So let's say they just happen to move all of their furniture out before going on vacation. Who does that? They would have to explain why they moved their furniture out of the house and why there was gasoline on the carpet and it lit right when they went off on vacation. So again, it's not just the presence of an accelerant that makes it arson, but the totality of circumstances in the investigation. The quantity of gasoline could be determined from the burn pattern on non-porous flooring as well. Significant quantities of the spilled fuel were present after extinguishment of the carpeted fires. So this melted carpet inside the donut protected the unburned liquid. And so this donut that they're talking about is this donut burn pattern. So if you have a pool of fuel right here on the carpet, it's not the liquid that burns, surprisingly enough. I mean, just think about your candle, right? You light a candle, and it's the flame at the wick that melts the candle, and then that liquid wax does not burn, right? If it did, the flame would go down onto the liquid wax, and it would just burst into flames. That would be a dangerous candle. It's the vapor that burns. Well, wax is just not volatile, so there's not a lot of vapor wax above the liquid wax. The liquid wax flows up the wick, and then the heat causes the wax molecules to decompose. So you have propyl groups and butyl groups and ethyl groups breaking off of these long 20 carbon wax molecules, and it's those smaller compounds, the decomposition products, that are actually burning in wax. Well, similar thing happens with gasoline. You pour gasoline on the carpet, and it's the vapor above the liquid that's burning. And the liquid will warm up, but it will not go above its boiling point, because that's just the way things are. I mean, when you boil a liquid, there's a temperature pause at the boiling point, and that temperature will stay there until all the liquid's evaporated. And so that boiling point of the gasoline or diesel will protect the carpet that it's soaked into. So you will, as it dries out, then catch the carpet on fire. So there'll be burned carpet around the outside, and then in the middle, where there's still liquid fuel, you will have liquid fuel and maybe some melted carpet fibers. But as long as there's liquid fuel in the middle, it's never going to go above the boiling point of that liquid. And so you will preserve some of the liquid accelerant in the center of this donut burn pattern. You put this fire out, there'll be a black donut, and maybe even some unburned, maybe even unmelted carpet right in the middle. We don't really see much of a donut pattern on the non-porous flooring. So you see that the flames are following the grooves in the wood you see here. But that just means that there's liquid underneath in those cracks. And so you might be able to pop some of these pieces of wood up, and on the back side you'll have some of the flame, some of the liquid accelerant. And so if I was coming in to investigate this particular fire, I would get my arson can ready. I would get a screwdriver or utility knife, and I would pop up the corners of some of these tiles and break that wood off and stick it in the arson can and seal it up immediately. Then maybe even put it in a freezer. So the peak heat release rates were examined on the non-porous surfaces, and these were about 1/4 to 1/8 of the heat release rates of a pool fire. So they can calibrate this with the pool. So if you have diesel and you put it into like a skillet, okay? So you have a pool of diesel in a skillet, and you heat that up so that it'll flash, and then you light it on fire, and so that diesel is burning in a pool of diesel, and you measure the amount of heat that's coming off of that. That's what's called a pool fire. And it's saying that on the non-porous flooring, like the tile flooring, the heat coming off of that fire was only about 1/4 to 1/8 of the heat released from a pool of diesel, because the diesel has soaked into the cracks of that flooring and is not able to burn as quickly, and it's just sinking the heat into the larger area. But for carpet, the heat release was about equal to a pool fire. So diesel or gasoline poured onto a carpet is just like burning straight gasoline. Now the evidence collection must be collected as quickly as possible and then put into an airtight container. Many times there's a little septum in the top, a little silicone rubber gasket, so that you could stick a needle in and sample the air space above the evidence. And so traces of these liquid residues may be located with a vapor sniffer or a dog. So you can have arson dogs that smell for gasoline, and they can find the accelerant if it's difficult to find the point of origin. You can also use vapor sniffers or gas detectors. And so it's also important to sample similar but uncontaminated control specimens. So if I were to use that wood flooring, like I said, I would collect the wood flooring where it was burned. I would pick some of those pieces off, put them in an arson can, seal it up. I would also go to a place on the floor that was not burned. This is really important. And I would pop some of those pieces off and put those in an arson can too. Because what if that signature that I'm calling diesel fuel was really just a treatment on the whole wood floor? Then I might suspect an accelerant when there really wasn't one, and I might be putting an innocent person in jeopardy of going to jail. Also, a search for igniters such as matches or some sort of sparking device, or maybe even parts of a Molotov cocktail. So maybe you've never heard of a Molotov cocktail. You see this in some of the riots that you might see on television, and it's gasoline or some sort of flammable liquid placed into a breakable jar, like a glass bottle. And then you light this match, and so the match is burning, and then you throw it, and when the glass breaks, then the flammable liquid is released, and it goes from just a match flame to a large burst of flames. And so that's called a Molotov cocktail. I'm not exactly sure where that name came from. Here's the evidence cans, and I think these are the best because they're metal. Now, when in face-to-face class, I would ask you to tell me why you think metal is important. But since we don't have the ability to interact here, the metal is important because it is impervious to gas. So you're not going to let the vapors escape through the walls of the container. And then here's that septum that I was talking about. This is a silicone rubber septum, and there's a pass-through, so you can stick a needle through the top of this septum and sample the headspace inside this arson can. Sometimes they'll warm up the arson can and make that accelerant evidence more volatile, and they'll pull the gas out of this can and put it on a gas chromatograph. There's nylon evidence bags too, but I don't like these because the nylon is potentially will potentially let vapors through, so it might let some of that evidence of a gasoline or something that's volatile escape through the bag. I think it's much more defensible to use a metal can rather than a polymer bag. So let's look at some of the different types of analysis techniques. Remember, let's just pretend we're trying to collect or detect gasoline. So how do we get gasoline from the surface of a piece of flooring like carpet and get that into our gas chromatograph so that we can analyze it? Okay, well, here's one way. We can take the evidence out of the evidence container, put it on a little heat source, and then we can have a little cover that that pulls that material off, and we call this some sort of trap. So this steam source is pushing steam, which is again the heat source, and it's pushing it onto a trap. A trap might be some sort of adsorbent material. So this is steam distillation. It's using clean steam to steam the volatile components off of our evidence and onto an adsorptive trap. It could be like molecular sieves or something like that sort. And then you would extract the evidence, the gasoline, if you will, off of the trap material into something that's very, very volatile, like a pentane. You would say, well, what if they used pentane as an accelerant? Well, pentane will boil in your hand. It is so volatile, it's not going to be useful as a liquid accelerant. And so you could desorb it off of that trap into a pentane distillate, and then you could run that on a gas chromatograph. Another way is to use solvent extraction. So instead of using heat to push it onto the trap, maybe you could just wash the evidence with a solvent like pentane or carbon disulfide. So carbon disulfide is a good solvent, although it's quite toxic. But it's also not going to be very useful as an accelerant. So it's not going to interfere with gasoline or hexane or diesel fuel, etc. And so you could put the solvent into the debris container, wash it, extract that, or pour that into an evaporation dish, evaporate it down, which will concentrate it, and then you can take it to the gas chromatograph. So this would be an solvent extraction method. These E numbers are ASTM numbers, and so these would be the ASTMs for these different techniques. You could just warm the container and use that septum, put a gas syringe in there, and sample the gas. This would be headspace sampling. So you can go straight from the syringe and inject like 1 milliliter of headspace gas right onto the gas chromatograph. You could use passive headspace absorption. So you could put a charcoal strip. Now charcoal has an enormous surface area and is very attractive to organic molecules. So first you have to activate it. So you heat this charcoal up to drive off all of the volatile organic compounds, and then you can place this charcoal strip in the headspace, and any of the volatile compounds will come off of the evidence and land on the charcoal strip and get stuck. Then you can extract that with an extraction solvent like pentane and put that onto the GC. You can use like a purge gas, so helium neon purge gas. So this would be called purge and trap. So you purge this through the container, and then you have an absorbent like charcoal, and then you have gas chromatographs that can put these absorbents directly into the stream, the elution stream, or you can extract the compounds from that absorbent using carbon disulfide and then put that onto the GC. And then more recently, this technique has really taken off. It's called solid phase microextraction. And so they have these silicon polymers like diphenylsiloxane, and you can have this little needle or fiber, and it's inside a little protective sleeve. So you have a metal sleeve that is strong and can go through that septum. So you will purge or punch it through that septum, and then you push down this little plunger, and this needle comes out that has a clean polymer on it. And the molecules that are in the headspace will stick to that polymer. And now these siloxane polymers are very strong and very temperature stable, high temperature stable. So they can handle the 280 degree inlet temperature of a GC. But the other volatile compounds will come off. So the volatile compounds stick to the fiber. You pull the plunger up so the fiber goes back into the metal sleeve. You pull that out and stick it into your GC inlet and push the little fiber down. And now the fiber is in a 280 degree inlet, and the volatile compounds come off the fiber and then go through the gas chromatograph. The SPME, solid phase microextraction, is a great technique. It's not very quantitative, but it is qualitative. So you will get a particular set of peaks that have a pattern related to diesel or related to gasoline or some other sort of combustible fluid. So let's look at some of the data that we get from these. In the laboratory, the gas chromatograph is the most sensitive and the most reliable instrument for detecting these flammable residues. And so, since most of these arsons are initiated by petroleum products, these GC traces the various retention times and the relative compounds. It's going to be like a fingerprint for the different materials. And so let's look at some of the liquids that have been analyzed on GC. So it also depends upon the technique, as you might imagine. So this would be the headspace solid phase microextraction, and you would see this pattern, say, from a particular fuel. And then the static headspace will have a slightly different pattern because a slightly different extraction mechanism pulled the different compounds in different concentrations. So the take-home lesson here is, if you have a database that was developed using dynamic headspace, you can't reliably use then solid phase microextraction to give you a perfect match on that. Now it's still going to show you several of the same peaks, but notice how they all have slightly different relative intensities. So this just means that if you're going to use solid phase microextraction for arson investigation, that you really need to set up a library of samples and do multiple runs on samples. And so you might have diesel taken 2 or 3 times and put into your library using SPME, and then gasoline, and then you may even want to do regular gasoline and high octane because they might have slightly different chromatographs. And so let's look at different kinds of things that we will see in the house too. Don't just do accelerants, but do things that might be also found in the house, like shoe polish or WD-40 or furniture polish or mineral spirits or maybe insecticide. And so here's a bunch of different household items, and these are the different chromatograms. And so you can see the different carbon chains that come off. This is a C10, a C11, a C12, and then various fragments due to different functional groups. You can see WD-40 is primarily C10, so 10 carbons, and then this might be a bit of an oxidized C10, so it's got a little bit heavier mass. Maybe there's some oxygens that have attacked that backbone chain. You have some C9 and C11. The propellant and rate insecticide, or the solvent that's holding the active ingredient, is a little bit heavier. Its major component is C13, but it's got quite a range of different carbon peaks. So most of these are hydrocarbons. You've got a few functional groups in there in the middle. And so you must have controls. These evidence images are also essential. You need to see the V pattern. You need to see documentation of the whole scene. And the thing is, it would be a travesty to arrest a good homemaker for arson. So if you saw, like it looked like the fire started on a piece of wood in the corner of the room, and you went and sampled that wood, and you saw that you thought it was diesel fuel, but maybe the good homemaker used lemon oil furniture polish. These are very similar chromatograms. And so you would want to find a sample of that wood object that was not burned and scrape some of that off, put it in the arson can, because that would give you the lemon oil furniture polish signature, and the burned area may still have some of the lemon oil furniture polish on it as well, and you might mistakenly say that that was diesel fuel. So that's what I mean by controls. You need to sample some unburned areas and some burned areas. And then your database back in the lab has to have as many household objects as you can, so that you might be able to rule out the diesel or gasoline if in fact it's WD-40. So arson investigation is one of the most challenging areas in forensic science. In the past, like more than 20 or 30 years ago, the conventional wisdom was if you saw crazed glass like this, or you saw spalled concrete, that was evidence of extremely high heat. And so they would label this arson because they thought that only in using an accelerant that would produce extreme heat conditions would you get these kinds of signatures. Also, melted metal. They said wood would not melt metal, and that's not true. My son and I do this in our backyard with leaves and sweet gum balls. We melt aluminum cans and pour it into muffin tins to make aluminum ingots. And it's the heating rate, not what you're burning. And so it's you can have flattened bed springs as well. Those used to be listed as evidence for arson. And then burning at the floor level. So you start out with a V pattern of the flames, but eventually the whole floor can burn. And they would say that that was evidence of arson because the floor didn't show a V pattern, that the whole floor was burned. But they have a condition called flashover. So the first you get a V pattern, then the ceiling catches, and then when the ceiling starts to decompose, then you have burning gases in the upper part of the room. And that's called flashover. So you just have this burning gas of decomposition products in the room. They're at the top of the room because heat rises. But then radiative heating from that burning fuel in the top of the room will catch the floor on fire. So radiative heating is what's catching the floor on fire, not convective heating. Convective heating is molecules banging into molecules, and that's what causes heat to rise. And that's why a convection oven has a fan in there. It's pushing air currents around. So convective heating burns the ceiling, but radiative heating burns the floor. And so you will initially see a V burn pattern, but then once you have flashover, then you have radiative heating and the floor can burn. A lot of these conclusions were overturned with some of the California fires, whenever they had whole neighborhoods burned to the ground because of some of these wildfires in California. Arson investigators were able to go in there. They knew that people had been evacuated from their homes, and so there was nobody there to set the fire, that this was just a natural external cause. And they went in and they saw crazed glass, they saw spalled concrete, they saw melted metal, flattened bed springs, floor level burning. And so it overturned a lot of this conventional wisdom. But it was sad because in the past, many people would be convicted for arson because of these naturally occurring phenomenon that were listed as arson by the conventional wisdom. So in the last 20 years or so, many of these indicators have been seen in non-arson home fires, and we have more accurate investigations. Like here's a picture of some of the thermal cameras and so on being used at the NIST Fire Research Facility. So hopefully you enjoyed this video on arson investigation. It's another area that you may go into with your forensic chemistry degree, and I think it would be an excellent use of your skills.